What we're going to demonstrate now is the essence of perpetual motion. And it's still a prelude to what I'm going to do with the generator and make it just run itself perpetually, and there'll be no batteries, there won't be anything. But I'm going to show you, even with the battery, it's perpetual motion. And nobody will be able to do what I'm fixing to show you. Nobody can reduplicate what I'm going to show you. So you know that it works. Now right now, I'm going to just check the voltage on this battery so that you can visually see it. And that battery is 11.87 volts. Now, what you're going to see, just so you'll know, when you put batteries, we have 10 batteries that's going to run Big Eureka in series. Now, when you put batteries in series, the current is equivalent to what's in one battery only. You multiply the voltage, but the current is of one battery. If you want to keep the voltage the same, you put all the batteries in parallel, and then you'll only have 12 volts. This is a teal motor, and when I hook it to this battery, it's going to make it plummet. This motor is bought from Granger, and it draws 10 amps under load. Now, I'm not pumping water because of the fact that it'll just kill this battery. Now, what I'm going to do is hook this to this voltmeter, and all I have to do is touch the voltmeter to the battery, and it will run the motor and show you the battery voltage at the same time. Now, you see it plummeting already. What's it on? Call it out. I can't see it.
11.4, 11.48, 11.49.
All right, now you can see how much.
11.48, 11.481, 11.47. 11.47, 11.46,
All right.
11.468, 11.461, 2, 7. It's kind of leveling off around there. No, it's down to 11. It's fluctuating down to 11.4.5, 0.45. 11.3.
All right, it's pulling that battery on down. It's the same thing that I have up here on this Granger catalog that's put out by the so-called experts. As they make this motor bigger, as this mass gets bigger, this is 89 pounds, and it draws 4.4 amps. If you're using 460 volts, and it draws 2.2 amps. Excuse me, 2.2 amps if you're using 460, and 4.4 amps if you're drawing 230. Now let's go on down to a 2,200 pound motor, and it's going to draw 225 amps. Now the heat loss in a motor is the current squared times the resistance. So your heat loss in that motor is very, very high. In some motors, they draw so much current, they have to have water or some means to cool it because the heat is so high. Now I'm going to run a 7,500 pound motor off of these batteries in series, and the current is equivalent to what's in one battery. You saw this little motor start bringing this down very quickly. What I'll show you is the essence of perpetual motion, because we will run a 7,500 pound motor, and we'll run it for 20 minutes, which I had already done. And then I had Jed come over and shoot it yesterday, because I knew that the battery voltage had gone back up overnight to 119 volts. And this graph right here will show you this result, okay? And you can see over here on this, if you pull it up, and the self-explanatory as you read this information of what is happening is we run the first test, and then we run the second test, and notice something. At the end of each test, the battery voltage was 118.4 volts. On both tests, showing that there was no voltage drop. And overnight, they'll both go back up, because the night before it went back up to 119 volts. And that's a dead volts. It's a float volts. Now when you put it under load, it pulls it down just like when you saw this little motor, and it's not even under load. That little motor pulled it down, this battery down. Yet a 7,500 pound motor doesn't pull it down. We run it for a total of 40 minutes, and that's what you're going to see now. And that's the essence of perpetual motion, because no one else can demonstrate to you what I now demonstrate to you. This is, again, the second part or the prelude to perpetual motion. See, the time is 2:17. That's PM. 118 to 117. All right, now we're going to let it run for 20 minutes. "20 minutes will be 237. We'll turn that off. But we'll check the voltage before we turn it off. Now it's picking that water up 5 feet. And you can see how big that diaphragm is back there. It's over 5,000 pounds. All right, we're gonna walk in the back. Now you can shoot all the way down this motor so they can see how big it is. This piston is a foot across. You got air pressure at 14.7 pounds per square inch. There's a steel plate underneath this rubber that this is bolted to. And then when it goes up and down, it's taking over 5,000 pounds because we're lifting this water 5 feet. Not 1 foot, 5 feet. If you were lifting it 1 feet, time you do the numbers on this, it's 1,160 pounds. Now you lift it 5 feet, it's 5 times that. All right, it's 237. It's fixing to be 238. He had to get his camera. And this water is fixing to come out again because it takes it a few seconds on each pump to get up there. But we'll check the voltage in the meantime. 117 to 118. 117 to 118. 117 to 118. 117 to 118. I was being very conservative when I told you the good battery is going to have 12.5 volts. That's true on the conventional battery. This tells you they charge this with a little over 14 volts. It's what they use to charge these batteries. And they'll be having 13.8 volts on the battery when it's fully charged, and it says so right here. And you verified that, correct?
Yes, I did.
Okay, and these are made for the military. That's why I bought them. They can take high surges of current without damaging the elements in the battery. And that's why that these batteries are still running, and this is running basically at the same speed it was when we started off. And we haven't hurt these batteries. And we'll check it one more time before we cut it off. $18, $117. There we go. And with that, we're going to cut it off.